people who eat breakfast for dinner. I don't really.
I eat breakfast. My kids eat like every week.
I don't care for breakfast food too much.
Yeah.
But you know, we don't keep a whole lot of breakfast food in the house because we usually don't have time to like sit down and make pancakes before we leave. We don't do that. We just have cereal and then we take it with us. So you know, we just heat up leftovers and eat them in the car. So like, am I crazy for eating
Yes.
pizza at 6 o'clock? If I'm crazy. Yes.
All right. Hey, I want to show you guys something because it'll be useful for you today. So matrix multiplication, which was one of the things you had to do for today, is almost fun.
No.
Almost, but it's tedious and error-prone. It certainly is easy, right? The whole matrix, multiply two matrices together. Here's the deal. Matrix multiplication is actually something that's a huge deal in lots of things of science and computer programming and so on. For example, when they do computer animation, okay, huge matrices with thousands and thousands, maybe millions of rows and columns, hold all the coordinates of Moana. All the little, you know, the corners of all the little vertices of all the triangles that make up Moana's body. And then they multiply it by another matrix that describes the location of where the sunlight is coming from. And the multiplication of those two matrices explains like things like the angles the sunlight is going to be hitting or something like that, okay? Matrix multiplication is a big thing, and it typically doesn't involve a 3x3 matrix in the real world. They don't really sit there and do all this obviously by hand, or even like with some little algorithm or something like that, and neither should you. You should at least have a way to check your work, and I thought I would just show you that if you use something like Google Sheets or whatever, there is a matrix multiplication function. For example, let's just make ourselves an annoying 3x3 matrix here. Here's a 3x3 matrix. And let's just give you another matrix here. How about this 1x3? First off, I'm sorry, 3x1. Can we multiply these two matrices?
Yes.
How can you tell?
Because they have the same number of columns.
The number of columns in the first one is equal to the number of rows in the second one. So it would work. And it turns out there is a function in any spreadsheet program called mmult. Okay? And it would multiply two matrices. Just like any kind of function in a spreadsheet program equals, and then the name of the function you want, in this case mmult. Alright? Now, notice by the way, okay, it'll give you tips if you need it with like the question mark here. I happen to have the tip turned off. But all you do for the matrix multiplication is you drag across the first matrix, comma, drag across the second matrix. And it'll fill it all in. Alright? This is pretty damn handy. Especially as matrices get bigger. Whether you use this to do the homework or whether you do this to check your work on the homework, I'll steer you different ways. But this is a tool. And I have no problem. Dig around in the Ivy Tech goals for the course, and use of a variety of technologies to solve problems involving finite math is buried in the goals someplace. Okay? I have no problem with you using tools like this. Alright? So matrix multiplication is a damn good tool to know about. Alright, I need to turn this off then for a little bit here. And again, I'd be glad to demonstrate, but you'll be shocked to discover we will be doing more with that later today. It's not a coincidence that I showed you that right now. Alright. Okay. So, we're talking about matrices and matrix multiplication and all that kind of good stuff. And that's actually a really powerful set of tools. Because we're trying to learn how to solve systems of equations. Something like 3x plus 2... Well, wait a minute. This business of x and y and z sure isn't very flexible. I mean, what if I had more equations? If I had 4 equations with 4 variables, how are you going to feel after you get to z? What's your next one going to be? If there was a system, if there was a problem that there were 4 variables, what you going to use after z? day? Is that what you said? Elapse? Here's a better idea. What if we did this? How about we call this x1, x2, x3, x4. So like maybe minus 11 x4 equals 17 or something like that. Are we happy with doing that?
It's kind of like more confusing.
It's kind of like more confusing, but you understand what I'm doing here, right? x1 is just, it's just a variable. x2 is just a variable. x3 is, it's just giving us an ability to have as many of these as we want, right? Rather than like we run out of letters of the alphabet or something like that, right? And I could have another set of equations here. How about x1 plus x2 plus x3 plus x4 equals 0? And I could have another equation here. How about x1 minus x2 minus x3 minus x4 equals 5? And how about another equation? How about 7x1 minus 5x2 plus x3 minus x4 equals 10? I'm happy. No, I'm not. I just made those up. But there are 4 equations with 4 variables. It sounds like Gauss-Jordan could solve this, although 4 equations, that would be a mess. It could be done. It sounds like elimination or substitution or one of those methods you learned in pre-calc could work, although that sounds like a mess. I'm going to show you a way we could get to this better. Let's make a matrix that just has all these coefficients in it. 3, 2, 3, negative 11, 1, 1, 1. Oh, wait, I missed one here someplace. Negative, yeah, no, that was right. 11, 1. 1, negative 1, negative 1, negative 1, 7, negative 5, 1, negative 1. Let's call it A. It's just got all the coefficients in it. What does this equation look like? It would be this number times x1 plus this number times x2 plus this number times x3 plus this number times x4 equals 17. How about x1, x2, x3, x4 equals 17, 0, 5, 10. Do you see how these two things are the same? This equation, and this one, and this one, and this one, are all here. I mean, let's just look at the bottom line here. 7x1 minus 5x2 plus 1x3 minus 1x4 equals 10. Do you see how that matrix multiplication is the same thing? We have replaced this messy set of equations with this. Hey, let's call this matrix X, like big X. And let's call this matrix big B. That ain't enough caffeine to get me through this day. Long weekend. In other words, AX equals B is another way of saying that whole messy set of equations over there. And here's the deal. This was 4 equations with 4 variables, but if this had been a million equations in a million variables, it would not be a different equation. The answer would still be AX equals B. And what we need to solve for is X. My student who is stressed about Gauss-Jordan method.
Yes.
When you have AX equals B, how do you solve for X?
Get A over to the other side.
You get A over to the other side. That's right. If this, forgetting this is matrices and stuff like that, Andrew, how do you get A over to the other side?
Just like basic algebra, just subtract.
Yeah, it sounds like you should be able to divide, right? Divide A by both sides. Here's the deal. There's no such thing as dividing matrices.
That sucks.
That does suck.
So
But
much-
realistically, there's got to be another trick. If this was AX equals B, and these were just numbers, yeah, I love that idea. Just divide by A, right? Another way to do it would be to say A times A to the negative 1 x equals A to the negative 1 b.
Isn't that basically the same thing?
Yes, it would be the same, right? Well, it does turn out there is such a thing as, we don't pronounce it to the negative 1, we would call it inverse. But there is such a thing as A inverse in a matrix. We're going to get there. That's what today is. Inverse matrices. But x equals A inverse times b is a thing. If we could get that inverse function, that inverse matrix, all we got to do is multiply it by b. How hard is matrix multiplication again? Not that hard, right? Okay. If we could get that inverse function there, that inverse matrix rather, we are gold. That inverse matrix is a handy-dandy little thing. It's going to have a nifty property. Whatever A is, it may have an inverse. I'm saying may, not all of them do. We're going to find out what kinds do and which kinds don't. But if it has an inverse matrix, A times A inverse is going to be equal to the identity matrix. Whichever, I'm making it 3 by 3 here, but it would be however big it needs to be. Where the identity matrix, I, is all zeros except down the diagonal is 1. That identity matrix is another way of saying the number 1. Any matrix, here I'll call it C, times the identity matrix, well I guess any square matrix, C times the identity matrix just gives you C back. It's a nifty little trick. So if we could get this matrix, this inverse matrix, we're going to be gold. Right off the bat, in order to, what kind of matrices are going to have an inverse matrix? Because not all of them do.
Wait. No, right? They
What?
have to be like the same.
They have to be square. That's right. For one thing, only square matrices have inverses. Also, in order to have a matrix, to have an inverse matrix, you can't have a row of all zeros. If you have a row of all zeros, you would be saying 0 times this plus 0 times this plus 0 times this times 0 times this equals 1. Well, that's a good trick. Right? You never get 0 times something plus 0 times something plus 0 times something equals 1. That's not going to work. So, 2 rules you got to know for sure. You'll only have an inverse matrix if the matrix is square. Good news is all of these ones that involve solving a system of equations, because they have 4 variables and 4 equations, or 3 variables and 3 equations, or 2 variables and 2 equations, or in the case of Moana's animation, a million rows and a million columns, but it's square. So that's usually not a very hard rule to stick to. None of the whole rows are 0 can break it. There are still other ones that don't have inverse matrices, but that's 2 important rules to keep track of at this time. I like this problem so much up here that I'm going to leave it up here for now. But let's do a simpler one first, and let's actually pick one out of the book. Hold on just a second, so that we're doing one that we know has an answer. How about... Nope, that's one that does not have it. Let's not do that one. Oh, hey, I want to show you on page 88. You have the book out. On page 88, notice that you have some problems there in example 1 that say verify that these 2 matrices are inverses. What do you suppose verify that their 2 matrices are inverses ends up meaning? Multiply them out. What are you going to get? If you get the identity matrix, they're inverses, right? If it says here's A, here's B, are they inverses? Multiply them. Okay? And if you get the inverse matrix back, great. Okay. So if you look at page 88, for example, they're actually showing there, here's a matrix and here's a matrix, show that they're inverses of each other. Okay. And they did A, B, and look, they actually got the the identity matrix, and they did B, A, and they got the A. So there you go. Let's actually figure out, though, how did they get this one? All right, so the matrix is 1, 3, 2, 5. Their matrix A is 1, 2, 3, 5. Did I have it right?
1, 3, 2, 5.
1, 3, 2, 5. There you go, see? 1, 3, 2, 5. How did they come up with that matrix? How did they come up with what the inverse is? I'm going to show you how you do it by hand to find the inverse matrix. And then I'm going to show you how to do it using a spreadsheet. Okay? Which answer are you going to like better?
This one.
Probably the, what? This one, not the spreadsheet one?
My spreadsheet.
I forget to do parentheses on spreadsheets and then I have to do it all over.
Oh my
I'd
God.
rather just write it out.
Alright, well, let me show you. Again, we did this actually in pre-calc, but it's long enough ago and abstract enough that you don't care. What you do is you make yourself a little fence here, just to help you keep it straight. And on the other side of the fence, put the identity matrix. Then, we're going to do row operations, as many as it takes, until we get where the identity matrix is on this side of the fence, and this side is whatever the heck it is. And this side will be the inverse. That's our goal. We want to do row operations on this until this side, instead of being the matrix we started with, is the identity matrix. So for example, I see my first target. If I were thinking about this, I'd try to get rid of this guy first. So like if I did some row operation where I leave the top row alone, but I'm going to get rid of this guy, how about 2 times this one minus this one? 2 times this minus this is 0. 2 times this minus this is 1. 2 times this minus this is 2. 2 times this minus this is this. So my strategy was to go for this guy first, although we could have just as easily gone for this guy first, right, to get rid of him. Alright, how about we go now try to get rid of this guy? Well, how about 3 times this minus this? 3 times the second row minus the first row. So I'm going to go ahead and copy that second row over because it's not going to change. 3 times the second row minus the first row. 3 times this minus this. 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 And we're getting pretty close. In fact, the only thing I think is I need to multiply that first row by -1 to change the signs, right? So let's try that. 1, 0, -5, 3, and leave the bottom row alone. So, if I did this right, since now this side is the identity matrix, this side should be the inverse. Is that what they got for the inverse? Oh, I didn't make a mistake there. This is pretty slick. Because, I'm going to put a little line here just to help me remember. Let's say our original equation had been x plus 3y equals 8. 2x plus 5y equals 9. We could call this ax equals b, where A is that original matrix, X is X, Y. I'm just writing this out, we'll talk about this in a second here. B is 8, 9. Do you see how if we had started off with this system of 2 equations and 2 unknowns, we could have rewritten it as AX equals B, where A was the coefficients, X is the variables, and B is the right-hand side. And we know that the answer will be that X is just A inverse times B. Well, now we have A inverse. That's -5, 3, 2, -1 times 8, 9, which will be equal to, let's try it. -40 plus 27 is -13. 16 minus 9 is 7. So the answer is 13. So x equals -13 and y equals 7. So solving this got a whole lot easier once we had that inverse matrix. But here's the deal. Those inverse matrices can be really hard. A 2x2 is no big deal usually. In fact, a 2x2 is never a big deal. As long as the matrix, as long as the inverse exists, like you don't have a row of zeros or something like that, that's not going to be all that hard. There are other reasons why it might not exist. Like if one row is just a multiple of the other, like if this was 1, 3 and this was 2, 6, you'll have a problem. You'll have a problem if you have a column of all zeros. There are other reasons why you might have a problem. If the inverse matrix exists, though, the 2x2s are easy. Even the 3x3s are doable. 4x4, it starts getting really, really hard. You're almost certainly going to make an algebra error. A 20x20, that is the matrix that some system of software is using as part of solving the solution of how they're going to schedule the delivery routes today on a UPS truck. And you're going to be doing problems like that later. Not today. It gets just, you're never going to get it right. So, what we need instead is a machine way of doing this. Now, before I get too far, I want to enter some numbers while I still have my numbers that I've been writing on the board. How about that system of 4 equations in 4 variables that we wrote up there on the board earlier? 3, 2, 3, -11. I'm sorry. 1, 1, 1, 1. 1, -1, -1, -1. 7, -5, 1, -1. And the right-hand sides were 17, 0, 5, 10. Okay. Let's put this back up. So remember this set of equations here. And we rewrote it in terms of... Let me scroll this over there so it doesn't have so much. Here is A. Here, I'll label it. This is matrix A. And we want to solve for X. And here's B. Alright, where X was X1, X2, X3, X4. It's the 4 variables. Woo! If you wanted to, you could do a 4x4 matrix by hand. But it is a challenge. You'll almost certainly make an algebra error. But how would you do it? You would start with this matrix, and on the other side, I mean, like you'd make yourself a little fence. I'm just doing it on a spreadsheet, but you wouldn't do it on a spreadsheet. You would make a little identity matrix of the same number on the other side, and you would do row and column row operations until you got the left side to be the identity matrix, and whatever's on the right side would be your inverse. But let me tell you, it's hard. It's a lot of steps. If you get bigger than 3 by 3, let's use the inverse function on your spreadsheet. I'm going to just label this here as A inverse. And the command is equals M inverse.
Are you going to share this document with
I can, if you want me to, yeah. And again, once you know M inverse, there's actually little tooltips you can follow. I have them turned off because they take up half the screen when you use some of these functions here. But just select the range that you're trying to get the inverse function out. And you have the inverse. Oh, that doesn't look fun at all, does it? Those are delightful numbers. Okay? So, remembering that x equals A inverse times B, I'm just making myself a note there. Let's actually do it. How are you going to do A inverse times B?
Equals
M mult for the matrix multiplication. A inverse, comma, B. And those are our numbers. That is the set of solutions, x1, x2, x3, x4, that makes that system of equations work. How did you feel about that compared to Gauss-Jordan?
Not easier.
Oh, yeah, how did you feel about that compared to elimination for a big matrix like this? Or back substitution? Or row echelon? Doesn't this, now don't get me wrong, behind the scenes, the math was huge that just made that happen. Okay, it's a lot of work. Who cares? It's a computer. I believe in making the computer work. I have this idea in my head that it makes computers happy. I don't know that they're doing their work for you.
Maybe when they come back and they roll the world.
Yes, or maybe when the robo-apocalypse comes, we're going to find out that the singularity and the computers are not happy that we're making them do our math for them. They're doing our math for them, for us rather.
Maybe they'll use that to their strengths and stuff.
That's right, and we'll all be too dumb to solve our own matrix problems.
Oh yeah, never the computers take over.
That's right. But here's the deal. A huge part of computer science is what you just saw. Okay? Every frame of every Pixar movie involves zillions of these operations. Every delivery truck that's trying to figure out where to take the routes to maximize their efficiency today is solving systems of equations like this. Every piece of software that is on some app that is figuring out a land surveyor how they're going to map out the spot is really doing this. Okay? The land surveyor is not sitting there going, oh man, well I guess this is a... No, he punches in the GPS coordinates of this and this and this and it figures out. They scan the barcodes on the deliveries that are going through on UPS, and the software is trying to figure out how to maximize their route, or minimize, or whatever you want to think about it, whatever. And it's a system of equations. And they're doing it with all these matrix inverses. Okay? It's in fact like the cornerstone of the information age. One of the cornerstones is matrix inverses. Because these kind of problems come up all over the place, and they're really hard to solve on paper. Once you get bigger than like the 2x2s, these start getting really hard to do on paper. You can probably do the 3x3s. If you're like super aggressive about it, you might do 4x4s. But even a simple delivery truck might have 100 packages on it that they've got to maximize the route, or whatever, minimize, or whatever. Even a really simple piece of video game animation that looks terrible will have a few hundred triangles that make up that character. All of the vertices of which have to be turned and multiplied, matrix multiplied to figure out where their shadows are and all that crap. Okay? This is a huge deal. Thankfully, you don't have to do it all by hand, even in a class like this. It's okay. So like even in a class like this, when you are doing the assignment, notice how I'm going to spell out for you. Well, 1 through 4 I think are verify type problems, where it's going to say, here's two matrices, are they the inverses of each other or not? Well, what are you going to do? You're going to multiply them. And I'll put this list of problems up on It's Learning too, in case you don't get them up there. 11 through 14, what I want you to do is to actually do the problem on paper. I think they're all 2x2 matrices. And I felt like everybody needed more practice with row operations. But I want you to check your answer with Google Sheets. Okay? You can choose to or not share those sheets with me or whatever. Probably a good strategy, though, would be to make a sheet that was called something like Day 7 in Finite Math or something like that, or Homework 2. Whatever we're on, 2.5?
Yeah.
Yeah. And just use it and share it with me at the end. Okay? But like 58 and 59, I think just use your spreadsheets, okay? I don't think there's any reason. If I remember right, 58's big. Well, big, like 5 by 5 or something like that. Let's see where we are. Page 94.
What should we call
58.
this?
It's 5 by 5. Oh, I don't care. I mean, just make your... But don't make like 6 different spreadsheets, one for each problem kind of thing. Worst case scenario, you guys know about like how there can be tabs at the bottom, right?
Yeah.
Yeah. Make a worst case scenario, just make a tab down here at the bottom for each problem. Or just make it use a scroll down, I don't really care, something like that, okay? I spend about 6 hours a day in front of spreadsheets and databases and stuff like that. You're not gonna overwhelm me with a spreadsheet with a couple of tabs, you know what I'm saying? You just see the stuff Mrs. McNamara sends me. She's got tabs and all kinds of crap all over the place. I mean,
Tabs and tabs and tabs.
and workbooks and all, there's all kinds of different ways they can be bound together and pivot tables and crap. Okay, I feel like we should do one of these though. How about problem 60? I have not done problem 60 yet. It's an adventure. I had a long weekend. I feel like an adventure.
Oh, that one was hard.
What? It looks hard?
Yeah.
It looks real.
That's the last thing he said before they snapped off.
And that's the last thing they said before they all died. Huh? It'll be an adventure. It's a manufacturing problem, if I'm not mistaken. And it says,
Apparently, Sarah's on her way home from Florida right now.
what the hell's that all about? She could have told me that. All right. Problem 60. Production requirements. An electronics company produces transistors, resistors, and computer chips. Each transistor requires boop of copper, boop of zinc, and boop of glass. Each resistor requires this much of the three materials, and each computer chip requires this much of those materials. How many of each product can be made with the following amounts of it? Oh! We're going to see something really neat about matrices that I forgot. It's even cooler. Oh man, I got to put that in the lesson plan.
Did you literally just...
I did! That is my contagious enthusiasm for this material. There's another really great thing about matrix inverses. What are we solving for here? What is X?
Units of copper.
No. How many of each of the things we can make, right? X is like number of transistors. Whatever, I can't spell today. Y is number of resistors. And Z is the number of chips, right? Alright. It takes a certain amount of each thing. So, let's see here. Zinc. Wait, which one's first? How about copper? So, we get 3 units for each transistor plus 3 units for each resistor plus 2 units for each computer chip. And we, in the first version of the problem, have 810 units to work with. Then, for zinc, we have 1 unit for each transistor. Each resistor has 2 units of zinc, and each computer chip has 1 unit of zinc in it, and we have 410 units of zinc to work with. And for glass, transistors need 2 units of glass for each one we make, and each resistor has 1 unit of glass, and each computer chip requires 2 units of glass, and we have 490 units of glass to work with. Oh, I'm so happy I could cry. This is a great problem. Because here's the deal. We're going to rewrite this as a matrix. This is going to be AX equals B, where A is 3, 3, 2, 1, 2, 1, 2, 1, 2. And X is little x, little y, little z. And B is 810, 410, 490. So, were we happy with this? A good solution would be that big X, which is what we're trying to solve for, is A inverse B. Let's go do this one. I'm not kidding, I'm that happy with this. Look. Somebody read me my A matrix there.
3, 3, 2.
It was a 3, 3, 2 or 3, 2, 3?
3, 3, 2.
3, 3, 2, okay. 3, 3, 2.
1, 2, 1.
1, 2, 1.
2, 1,
2, 1, 2. And read me my B matrix.
2. 8, 10. 4, 10. 490.
490, okay. Alright, so I know I need my A inverse. I'm going to have my X equals A inverse times B. So I know I need A inverse. Equals M inverse of this bad boy is, here he is. Okay, fine. So, I now have made my A inverse matrix. How about A inverse times B? I'm just making myself a little note right here what this is. And it's going to be the matrix multiplication of A inverse, comma, B. And there it is. Here's X, here's Y, and here's Z. We can make 100 transistors, 110 resistors, and 90 computer chips. So happy, so happy. We solved part A. Now it's time. MJ, are you ready to be impressed? Hallie, are you ready to be impressed? This is going to be awesome. Watch this. Look at part B. Now we have a different number of copper, a different number of zinc, and a different number of glass. Gosh darn it, we have to do all of that Gauss-Jordan again.
Are you going to say, but wait, there's more?
But wait, you don't have to. Because look, all we've done is change B. We already have A inverse. The hard part's already done. All we got to do is multiply A inverse times that new B. All we have to do. Can you feel the success?
Yes.
All of a sudden, something that was never possible with other ways to solve the system equation is suddenly possible. All I've got to do is put new values in for the B matrix. What is it? 765 and 385 and 470. And look, we have a new answer. And in practice, by the way, that's how things work in tons of kinds of problems that involve this system of linear equations. That's one of the reasons why the matrix inverse way of doing this is super cool, because once you've done the heavy lifting of computing the inverse matrix, all you do, so when they're trying to figure out where Moana's shadow is, and they just got to change the answer to like where the light is or whatever, but once they've already figured out the inverse matrix of all our coordinates or whatever, all those calculations are not having to be repeated. Otherwise, oh my word, it would take forever. When they're doing all those, figuring out all those package routes and stuff like that, once they have one time figured out that inverse matrix, all they got to do is plug in new things, like new information about where the deliveries are. This is one of the really super slick things about using the matrix inverse way of doing it. It's a lot more work. Behind the scenes, there was a lot of math. I mean, that 4x4 matrix wasn't the end of the world. A 25x25 matrix, ouch. A 1000x1000 matrix, Pixar might have been grinding for a half hour to make that one inverse matrix. But once they have it, happy. Now all kinds of good things can happen. Oh look, and we can do C. 1,010 units of copper. And, what was the next one? 500 units of whatever, zinc. And 610 units of, and look, it all changed again. Because as long as it was just this matrix times this one, I didn't have to redo all of this. These matrices contained all the constraints, like how many units of copper it took and how many units of zinc it took and how many units of glass it took. None of that changed. All we changed is how much we had available. The next day when you got a different amount available, we split those numbers in. We don't have to do all that heavy lifting the second time.
So this could be used to solve all the things that we were doing by hand with Gauss-Jordan.
Sure could.
They really need to change how they did these tests.
I'm not gonna lie. I kind of agree. I am so happy that we looked at problem 16 that I'm adding that to the lesson plan for today. Next time we teach this class, we're doing it too. Show them problem 60. It illustrates how wonderful
You should just say it makes me happy.
it is that you can reuse the inverse matrix over and over.
You should put a smiley face.
All right. So you've got the problem set for today. I guess I had it up there on the lesson plans here. You're good. Why don't you guys work on that for a while?
Should we do the exit ticket?
I'll give you the exit ticket in a little bit. I want you guys to get a little bit of miles on actually doing some of these before you see the exit ticket. All right, I'm going to stop this over here for Sierra.